Hello everyone. From the last two video, we are working on the simplification of circuit process. So in the second last video, I have told you about identity and how absorption's law work. And in the last video, we talked about the DeMorgan's law, DeMorgan's two law. So these all things are used in circuit simplification process. So if you have not watched those videos, so I would definitely recommend you to watch that video first, then only you can understand circuit simplification process. So, before starting the circuit simplification process, let me remind you one thing. Since we have looked at only one variable's absorption property, so let's see how it works when we are having the two variables. So suppose we are having AB plus A bar B. Suppose we are having this Boolean expression. So from here you can say you can pull B as common definitely, and then it will become A plus A bar. As I told you, A plus A bar is equal to what? It is always equal to 1. Because if A is 1, then it is 0. 1 plus 0 is 1. If A is 0, then this will be 1. So it will always be 1. So from here we can say that B into 1, which is equal to B. So if this is the condition, then we can pull out the common term and see whether we can get a logic to minimize those circuit by using these properties, various properties, or DeMorgan's law, distributive properties, commutative properties, or associative properties. So we can utilize those properties to simplify it further. Moving further, let's look at some more example. So suppose if we are having a question like A plus B and A plus B bar. In this case, can we take common? No, we can't take common, right? So what we can simply do is so we have to simplify this circuit. This circuit is using and OR gate. So let's see how we can simplify it. But before simplifying, let's check how this circuit look when it is in its original form. So this is OR. So if this is A, this is B, so we are having an OR and this is output 1. And what is this is also OR A and B is connected with a NOT gate, and then they are combined connected with an OR gate. Now the output of these two are connected with an AND gate. So from here you can say that how many gate we are utilizing. We are utilizing 1, 2, 3 and 4. In total we are utilizing 4 gate, right? So can we reduce the gate? Can we make a circuit so that we can have to use very less gate as possible, because in real world each gate cost us some dollars. So let's see how we can do that. So starting with this, can we do a direct multiplications here? Yeah, we know that it is just a normal mathematics only. So we can multiply a into a plus a into b bar plus b into a plus b into b bar. From here, do you see any pattern? We used that means, do you remember? We told you that a dot a is what? It is always a. Means you can multiply a multiple times, it will always result into a. While b dot b bar is what? It is always 0. As if b is 1, then b bar is 0. If b is 0, then b bar is 1. So it will always be 0. So can we utilize those logic here? Let's see. So this is becoming a and this is same plus b a or ab. We know that it follows commutative property, so changing order will not affect. And this will be 0. So now can we take a as a common from all three? Yes, we can take. So it will be equal to 1 plus a. Oh, sorry, a already we have taken common. So can I use an eraser here? Okay. Yep. So let's see. A plus b bar plus b. So just now we discussed that okay, a plus a bar is equal to 1, or no, we will not be using this. Instead we will be utilizing, since you can see this is an OR gate and we know that anything which is attached to OR gate, if a input is 1, then the resultant input will always be 1. It will be nullifying this thing. So you understand like this. Suppose these are three input which are connected to OR gate, and if this is B and this is B bar, and if it is 1, so so one will always be nullifying these two and our resultant output will always be 1. So from here we can say that a into 1, which will be equivalent to a. So from here we understood that whatever will be the input of A or B, our resultant output will always be A. So we don't need any of this gate because it is simple. If you are feeding A as input, you will be getting A as output. So how many gate required to perform this logic? We required 0 gate. So now, till now we have performed our operation using two variables or two input. Now let's try it with three input variables, means Boolean expression. So let's see if our equation is a bar, b bar, c bar plus a bar, b bar, c plus A B bar C bar plus A B C bar. So this is the circuit where we are having AND gate, AND gate, AND gate, AND gate, and they are connected with OR gate finally. So now let's simplify it. So if you see, can you see something common here? Like, can we apply distributive properties here and here? Yeah, definitely we can apply. So from here we can take common as A bar, B bar, and it is C bar plus C. Plus here we can pull out A C bar and it will be B bar plus B. So we know that C plus C bar is 1, same as this. So A bar B bar plus this has become 1 because we know that A plus A bar is 1. So this has become 1, this has become 1. So our next answer will be A C bar. So do we have anything which we can take common here? So here from here, can you see anything common here? So we can perform not common, but we can more simplify it using DeMorgan's theorem. Can we apply DeMorgan's first law here? DeMorgan first law, which is A dot B, or to be precise, we can utilize DeMorgan's second law, not first law, because we will be moving backward. So, wait. We will be utilizing DeMorgan's second law here, which will be equivalent to A bar dot B bar equal to A plus B bar. Although it looks more simplified, but we can move further ahead and it will be equivalent to A bar dot B bar A plus B bar plus A C bar. So this is the final simplified circuit. So if you see here how many gate we were requiring, if you want to count, so we were requiring uh, AND gate 1, AND gate 2, AND gate 3, AND gate 4. So total AND gate as 4. How many NOT gate? 1, 2, 3, 4, 5, 6, 7, 8 NOT gate. This is AND gate, this is NOT gate, and how many OR gate? 1, 2 and 3 OR gate we are utilizing. Or sorry, not 3. We can use it one time only. Na? So 1 OR gate we are utilizing. So from here you can say that we are in total utilizing 8 plus 4 plus 1. Or if we count, we are taking from one input and not making multiple NOT gates, so we can reduce the NOT gate count also, but there will be AND count as 4 and NOT count if we consider A, so we can utilize 1 and 2 and 3 NOT. Yeah, 3 NOT is sufficient here. We can make it with 3 NOT and or we need 1. So how many is 4 plus 1, 5, 5 plus 3, 8 gate in total we require to make this circuit. But now if we see how many gate we required, so A plus B, it is one OR gate, then one NOT gate, and here one NOT gate. So how many NOT gate required? 2. How many AND gate required? 1. And how many OR gate? Here 1 and here 1. So 1 plus 1. So how many? 1 plus 1 2, 2 plus 2 4 and 1 5. So we are reducing it to 5 gate instead of 8. So we are saving 3 additional gate. It seems like very less, but when you are using the circuit in bulk, then this number can be pretty high. Now let's look at one more question. I am solving more and more questions so that you can understand how we are simplifying the Boolean expression. So this is A plus B and A bar plus B plus C and C bar. So this is our question. Now if we apply distributive properties, so we can multiply it all like A bar, C bar, right? Plus A, B, C bar. Okay. I am multiplying this, then this, then this. Okay. Now A, this, then this, then this. So plus A, oh sorry, not double A, C bar plus now multiplying with B, A bar, C bar plus B, C bar plus C bar. Now from here, do you see a pattern? We can in fact cancel out many of them because we know that A bar equal to 0. So from here, can we cancel it? A bar 0, 0 into C bar is 0. Can we cancel it? C bar is 0, 0 into A is 0. So we can also cancel this also because C bar is 0, right? So if we come to the more simplified equation, so from here we can say A, B, C bar plus I am writing in proper order A bar, B, C bar because we know that Boolean expression follows commutative property, so we don't have any issue with that. This is done. Now this is A bar, B, C bar, right? Wait. Did I miss something? Yeah, I am repeating same thing. Sorry. So this is done. Now B dot B is what? It is B. So we will be having B C bar done. So now we have reduced to only 3. X means the 3 AND gate plus 1 OR gate. So now let's see if we can do any further changes or not. So from here, can we apply a distributive property here? Because we see BC bar common in 3. So let's take common as BC bar, and here it will be A plus A bar plus 1. As we know that A plus 1 is always equal to 1, so can we optimize it to 1, and our final result will be BC bar into 1, which is equal to BC bar, right? So from here to here, now how many gates required? We can make this circuit using B and C and one NOT gate and combine with the AND gate. So see, only 2 gates are requiring now, while previously how many gates were required? Here it is OR gate, then here it is OR gate, then here it is AND gate. So OR or 2 plus 1, 3. 3 gates are already there. Then internally OR 4, here internally OR 5. Like there's lots of gates are required, right? So instead of that, we have minimized it to 2 gate only. So I am also giving you one question to practice. Let's see if you can solve it or not, and do comment it. I know you can't make bar sign, but wherever it is bar, you can definitely put a semicolon. Yep, semicolon of what? Yeah, apostrophe. I am very confusion with I have a very confusion with this sign and all. But yeah, apostrophe you can put. So I am giving you a simple question. So this is A, B bar, C. Okay, and we have a bar here. C, A, B bar, C, and we have a bar here plus A, B, C. Please reduce it and provide answer in the comment, so that I can check it, and I will give a heart sign if the answer is correct. And also pin the first comment whichever is correct so that everyone else can also see it. Now this is not just a only method of simplifying the Boolean expression. There are various other methods which can be utilized to simplify the Boolean expression. So I will make a separate video on all the method for simplifying Boolean circuit. For convenience, I will be writing their names here, and I will be covering each and every method line by means video by video, one videos like that. So here we have utilized various law, DeMorgan's law, and various identities. So we will be looking at various other simple methods to make this process quicker, because for now we can see that the expression are slightly simpler, but there can be more complex expression where you can be seeing like this much or BCE variables. Like currently we are utilizing only three, right? But there can be multiple input also. So for those, which other methods, means there are other methods which can be more easier and quicker to simplify the circuit. So we have lots of method to simplify. Got it? So out of those method, I will be covering 2 to 3 methods only, so that it will be easier for you to remember also and to implement it, as all other methods are not used most often, and you can learn it while using it also. So what all method I will be covering? So first method is algebraic manipulation. So it is already covered, which we have done now. This is algebraic manipulation method. Next method is Karnoff maths, or it is popularly known as K-map methods. So this method is popularly used. It is a very quicker method. Mostly you can minimize the circuit till the 4 input, or you can minimize it as many as, but it is more convenient if you are having 4 input, and means 4 input means 4 variables. So for 4 variables, up to 4 variables, I mostly use K-map. Beyond that, tabular method is one method which is slightly lengthy but will give you result. Tabular method of minimization. So I will be covering this method one by one, since we have already covered algebraic manipulation. In the next video we will cover K-map, and then after that we can cover the tabular method of minimization, because this method I will give only one example, as this method is slightly longer and more of procedure based, and you have to follow each and every steps properly, then only you can understand. Same thing with the K-map also, and you have to stick to some logic, some uh, mapping, means you have to map the corner, or you have to map cell accordingly, and then only you can minimize the circuit. So before starting Kmap, I will be also telling you about SOP and POS. So what is SOP? SOP is sum of product, and POS is product of sum. So we can apply Kmap only and only when we have either of this. So I will let you know how we convert them into sum of product or product of sum accordingly. So we will see this all in next video. So till now, if you understand how we simplify this circuit, so you can like, and if you want to make means if you want me to make more videos like that, so you can always subscribe this channel. Means you cannot subscribe it multiple times, but yeah, one time at least. You can share this video with your friend, and if you have not got anything from this video, you can dislike the video. And yeah, I have shared one question with you. Don't forget to answer this question in the comment, and I will share a heart, means heart sign, so that people can know that particular answer is correct. So I will meet you in next video where we will be discussing more about key map. So thank you. Watch you means meet you in next video. Thank you. Bye.